When using a computer, multiple programs can often be found running at the same time. Perhaps one for playing music, another for creating documents, and one for browsing the web. All of these programs have certain functionalities, but on their own they do nothing. To actually make use of them, they must be executed. While a computer program is a static collection of coded instructions stored on a disk, a process is an abstraction representing the program when it is running. A process is created when a program is executed. These processes are not only central for the usability of a computer, but they are the building blocks of an operating system. Managing these processes is central to operating system development. Processes can sometimes also be called tasks or jobs, although these definitions are ambiguous. The key defining factor is that processes generally operate independently and do not share data. For example, a music player program will launch a music player process that would be independent of the process managing an Office suite. To optimize process performance as their priorities change or while waiting for limited resources, processes are categorized into one of 5 states. New: the program has been initiated and is waiting to be loaded into memory to become an active process. Ready: the process is fully initialized, loaded into memory, and awaiting the processor's attention. Running: the process is currently being executed by the processor. Blocked: the process is waiting for a contested resource to become available. Finished: the process has completed its execution. A process moves through these states, starting from new and ending at finished. Traditionally, CPU cores could execute only one task at a time, so managing process states helps the processor efficiently switch between tasks and share cores and resources among multiple processes. For example, instead of keeping a process in the running state while waiting for user input, it is marked as blocked, allowing the processor to focus on other processes in the ready state until the input is received. Blocking is not necessarily detrimental, as some tasks require longer processing times. By marking these tasks as blocked, the processor can prioritize other tasks, improving system responsiveness and efficiency. Additionally, processes may be moved to the ready state through preemption, where an external scheduler temporarily interrupts tasks for urgent needs, such as handling a hardware interrupt signal. However, switching between states involves overhead known as context switching. This process can be costly because it requires saving the current state of a process and then reloading it later to resume execution. When a process is created, its memory layout is divided into 4 key sections. Text section contains the compiled code of the program. Data section holds initialized variables. Stack used for local variables defined within functions. Heap manages dynamic memory allocation. Each process is also associated with a process control block, PCB, which the operating system uses to manage and track the process. The PCB includes Process ID, a unique identifier for the process, including the ID of any parent processes. Current state, the current status of the process. Runtime information, how long the process has been running and any associated time limits. System resources, allowed system resources and permissions. Priority, the process's priority level. Program counter, the address of the instruction currently being executed. Register addresses, locations of other CPU registers holding intermediate values. Memory management, details such as page and segment tables for memory management. Additionally, when a process initiates another, a parent-child relationship is established. For example, if a music player process starts a new process to scan the music library, both processes share resources and permissions. Typically, parent processes wait for their child processes to complete before terminating, unless the child was designed to run independently in the background. A process is an abstract data structure containing all the necessary information to run a program, whereas a thread represents the actual sequence of instructions being executed by the processor. Each process must have at least one thread to perform execution, though additional threads can be created for concurrent processing if the CPU supports it. Threads within a process share common resources such as memory pages and active files, as illustrated in the image to the right. Threads are defined by their shared resources. While processes are generally independent, multiple threads within a single process work together, enabling faster communication and context switching compared to processes. This efficiency comes at the cost of using fewer system resources. For instance, in a video game process, multiple threads might manage different aspects of the game, such as one thread for handling user inputs and another for generating sounds. Since these threads operate within the same process, they can efficiently share information about the game's environment. For example, the input thread can inform the sound thread about the type of terrain the player is on, allowing both threads to work together seamlessly to adjust the character's movement speed and corresponding sound effects. Multiprocess. Multiprocess refers to the use of multiple independent processes running simultaneously. Each process operates in its own memory space and resources, which isolates them from each other. This isolation ensures that a problem in one process does not directly affect others. However, communication between processes can be slower and requires specific inter-process communication (IPC) mechanisms. Multi-thread. Multi-threading involves multiple threads within a single process running concurrently. Threads share the same memory space and resources, allowing for faster communication and less overhead compared to multi-process systems. Since threads within a process share resources, they can efficiently collaborate on tasks, but they also risk affecting each other if not managed carefully. Process scheduling refers to the method by which the operating system decides which processes run at any given time. It involves managing the execution of processes to ensure efficient use of the CPU and system resources. The operating system uses various scheduling algorithms to prioritize processes, allocate CPU time, and handle multitasking. Process scheduling involves the operating system's strategy for managing process execution and ensuring efficient CPU use. Various scheduling algorithms are used to determine how processes are prioritized and allocated CPU time.